just talked to Mo Sharp, and he said he might be planning this one.
Okay. Well, before announcing our seminar speaker, I'd like to say I'm pinch hitting today, so I am not to blame for the lack of beer. Our seminar speaker today is Dr. Daniel Wormser. Dan received his bachelor's and PhD degrees from Johns Hopkins, working in the area of quantum gravity versus PhD thesis. The last 2 years he's been at the La Jolla Institute, which is located in beautiful downtown La Jolla, and all of us must be jealous of being able to work there. And the work he's done today is, he'll be describing today, is on rough surface scattering theory. It's for general application to acoustic or electromagnetic problems. And it's a project that he's been working on for 2 years in collaboration with Roger Dashen, whom I think many of you know.
Okay, well, thanks a lot. Okay, so as Paul was kind enough to say, I'm going to be giving a talk today about a new theory for scattering from surface. And that's work that I've done with Roger. And I got to do a little bit of it too over to La Jolla Institute. So now, give you an idea of what I'm going to be up to here. First, I'm going to give you an idea of, well, I'm going to cover about 100 years right here, and just say what happened with the theory when Kirchhoff first introduced it over 100 years ago. Really, it's been kind of an on and off, hot, cool topic in physics, and really went out of favor for a long time. But now, it's once again a little more. There's a little more interest in it. I'm going to sort of establish the formalism, and we're going to try to do that in a real physical context, explain what the formalism means physically, and describe the old theory. And by old, I don't just mean 1920s or so, but I also mean some of the things that were done in the 70s and 80s, and try to give you an idea of why what the shortcomings were of that theory, and why this is of more interest now. And I'm going to describe a new formalism that, well, I guess the real mover, shaker behind it was Roger Dashen. The new formalism really has two main parts. One is the theory for perturbations around a smooth surface, basically a formal description of what's going on there. And then you can use this. This is really the engine that will drive everything I'm going to talk about afterwards. Once you have this, one can use this to derive a new expression for the scattering amplitude that has a number of nice properties that I'm going to describe. And I'm going to go further and use this new formalism to, along with, in one case at least, the new iterative formula. I'm going to recover a lot of the old results here with virtually no work. And I'm going to go on and derive what I call a new expansion into curvature, and I'll explain what that is, why that's better, and how you get it. And talk about one of the problems that starts to show up with certain kinds of surfaces, and try to give you an idea of what the formalism is all about by discussing how we get around the problems and how we solve those problems. Okay, and then towards the end, I'm going to probably run through this fairly quickly. It turns out that, so here I'm going to just try to develop all of these concepts for the simplest possible case I know. Basically, solution to the wave equation, scattering off the surface. The surface boundary conditions are just that the scalar solution to the wave equation is equal to 0 on the surface. And then I'll generalize this. In the more general case, we have a scalar field, and you really don't care what the boundary conditions are. And also going to discuss the same kind of situation for the electromagnetic field, or at least mention that, yes, we have done it, that it's similar, and give you an idea of what that's about. And also show you how, or time, how you can get the expansion curvature in these three special cases.
The top one then is a scalar like the sound wave off the free surface, assuming no propagation into the air.
That's right. That's right. You assume, and when I say pressure equals surface, we're just talking about the fluctuation as the background pressure is constant. And in fact, what I have right there is the basic formalism. Okay, you have a scalar field P function of the position somewhere in the scattering region and the time. And for the moment, I'm going to consider just a finite scattering region, say some kind of a rough bubble or something like that, somewhere embedded in say, water. Later on, one could just as easily do an infinite surface. An example of that would say be an air-water interface. Okay, and S is, in general, some kind of a rough surface, although, of course, you can always use this kind of theory to do a smooth surface like a sphere or a hemisphere or something like that. Okay, so formally, you say a scalar field obeys the wave equation. Well, this is the wave equation. And for now, we're going to assume that the velocity of propagation here is a constant. We'll be able to relax that condition a little bit later on. Okay, and as you can see, this is the boundary condition on the surface S. And this is known as the Dirichlet boundary condition. And of course, the first step is that you want to use Fourier decomposition to make the problem time independent. And I'm sure everybody's seen this kind of thing. You just break this P of RT into components that are only a function of the position and some kind of incoming wave vector K. And we normalize the incoming wave vector to 1. And the frequency of each component is related to the velocity of the wave vector, like that formula. And so what happens is that this solution here satisfies the Helmholtz equation. Okay? And if the boundary conditions don't vary with time, well, then we're lucky that each of these individual components also each individually satisfy the boundary condition. Okay? Now, to do this kind of problem is, of course, very hard. That's why we have an asymptotic theory. And basically, the idea behind the asymptotic theory is if you can consider the scattering surface to be contained within a sphere of radius d, and then you assume you're in a region where your distance from the origin, which you define to be inside the surface S, the distance from the origin is much greater than d, then you get, once again, asymptotic results that I suspect everybody has seen before in a college course of quantum mechanics or wherever. Effectively what you do is you get an integral equation which reduces to the asymptotic region to something of this basic form. An incoming wave here normalized to unity, some scattering amplitude here, which is only a function of the direction, but not of how far out you are, and then basically the form of a spherical wave out at infinity. And we have the cross-section is equal to the magnitude squared of the scattering amplitude. Now, in quantum mechanics, of course, or a lot of these theories, they say, okay, complex wave, and that's just the way the world is, and so on. Here we really are doing a real field, classical field. There's nothing, no fancy profound physics. There's profound physics, but there's no fancy modern non-classical physics there. It turns out that you can use, of course, this kind of complex formalism, provided that you remember you average over several time oscillations. You get this kind of thing. And also that you can even see the phase of the complex wave. There are certain experiments you can do that. It just falls right out of the formalism. Okay, also now, formally, it turns out that if you actually go through, look at the integral equation, you can write this kind of an integral expression for the scattering. Now, the real quantities that define what we're looking at are these things here, the incoming wave vector k and r hat. And incidentally, this k is observable. You typically, when Fourier decomposes incoming and outgoing waves. Okay, so we have really this picture that we use, where we have k, and then we define this vector q, that's sort of the magnitude of k times a unit vector in the direction of the point of observation. Okay? And the reason it's so useful to do this is there's something called the reciprocity theorem. It basically says whether you come in this way and go out that way, or just reverse the whole problem in time, just come in the opposite direction, you're supposed to get the same answer. And this is just a nice way to summarize that. So that from now on then, I'm going to always talk about the two variables that are going to characterize the cross-section of the scattering amplitude to be k and q, okay, an incoming wave and an outgoing wave. And it just turns out to be useful. Instead of using version 1 of the scattering amplitude f here, you multiply it by 4 pi 2. So from now on, I'm talking about this t sub qk, and this really in the asymptotic region gives us all of the information about the scattered waves we might be interested in. Okay, now, as I said, this kind of thing is applicable to an infinite scattering surface too, which is really kind of surprising because you're never far away. And the bottom line is that you have to be very careful about what you mean. And just very roughly, and I can't really go into the details here, very roughly, you combine these Fourier components into a wave packet, and the idea is that in any real physical case, you're only going to see a small part of the surface. Effectively, then you can replace the surface away from the physically observed region with a flat surface, as long as you're careful about edge effects, like that. But and when you use this model, of course, the specular mirror-like reflection comes from everywhere. But you don't consider that, or that's sort of part of parameters of the problem. The mirror-like reflection is sort of the big thing that you automatically see anyway, and it's not really of all that much interest in our case. So we're only concerned with non-specular reflection, and effectively it only comes from a small patch. If it's from a small patch, then of course it can be way out in the asymptotic limit, and then all of a sudden all of these approximations you use to develop an asymptotic theory also work here. Very careful. Okay. So now the old theory, as I said before, started with Kirchhoff in 1882. And the bottom line is you need to find an expression for this kind of a scattering amplitude. And the way you do that is that you can start off with, again, the integral equation for the wet field anywhere. And then just be careful, take the limit as you approach the surface. A few funny things happen. But you get some kind of integral formula for this guy evaluated on the surface. You solve this integral formula, get sort of a perturbative expansion of this guy, put it back up here, and then you get a perturbative expansion of, an expression for the scattering. Okay? Now when you do that, go through that whole procedure, what happens? Well, very roughly, you can think of this as an expansion in the wavelength of the field divided by what's called the radius of curvature of the surface. Okay? This is a very good approximation in the high frequency limit, when you can see that you've got a high frequency of an incoming wave, and the surface looks like a gently sloping irregularity, and you have a very large radius of curvature. And of course, lambda over r will be small. Okay? Also, the other extreme is really not of all that much interest. The other extreme of the field is much greater than the surface. You have geometrical optics, and that's fairly well understood. What is a problem is what's called the low frequency limit, which is in between those two possibilities. In other words, when the wavelength of the field is approximately equal to the wavelength of the surface. Okay, and this is kind of tricky. And to explain how you go about that, I'm just going to very quickly introduce just a little bit of notation here. It's really useful to parameterize the surface this way. You have an xy plane, and then the z component is given by some function of x and y. Okay? And then I always use x and y as sort of a two-dimensional vector. I'll underline that. And if I have a three-dimensional vector, I'll put an arrow on top. Okay? Okay, so now, to do this low frequency limit here, what you need is at least first order in h. Okay? So the idea is you go back to your integral formula for n dot grad pk of s, as before, and you iterate once. Okay, now, it turns out there's a kernel to this integral formula that depends on this difference, h of x minus h of x prime. And you have to go through the whole process of expanding that to first order, looking at all the cancellations and so on, and then substituting that in the scattering amplitude. Parenthetically, it's kind of a nice thing to notice about this difference here, is that effectively what you're really doing is you're looking in derivatives of h. You're looking in the slope and the curvature and higher order derivatives. So in a sense, you've taken h itself out of the expansion. That would say be the difference between what's called the Born series, where you expanded everything. Okay? And, okay, now when you do all this, you get what's called a small slope expansion. The earliest reference I could find to that is by Milanovich in the early 1980s. So that you get this expression here. And you notice how this expression now, unlike the thing I flashed on just a minute before, this manifestly exhibits reciprocity. You can see that you put k, you exchange k and q to minus k and minus q. In fact, this has the right property. Whereas if we only did one iteration, it would not have. Okay. Now, if you're going to deal with a rough surface, the idea is you've got a full spectrum of surface waves. That means really somehow you have to combine high and low frequency results. Okay? And the way this is done is the composite model. Lots of people have worked on this over the last 20 years. There are a couple of nice papers by Suzanne McDaniel, which I can give you a reference if anyone's interested in. The basic idea here is you have a cutoff, I call K sub C, and you separate the surface into two types of waves. If the wave number of the waves on the surface is greater than K sub C, you have small waves. On the other hand, if the surface wave number is smaller, you have what are called, you have big waves. So you can sort of view the surface being made up of small waves riding on big waves. And again, formally what you do is you have H, you separate out into the big waves and the small waves, which again you can just see as just two types of surface, a reference surface and then the change, to give us the total surface. Okay, now, the next step is to say, okay, well, what are these big waves going to do? And, well, really all they do is they tilt the surface, first order, okay? So you just replace, instead of saying you're going to take the Z components in the small slope result I said before, you're going to start just taking the components as if, instead of Z hat here, you have the normal pointing out, okay? Well, just to briefly give you an idea, just to digress, to give everybody an idea of the physical picture of what's really going on here. What happens when you have the composite model? Okay, we get a slowly varying factor here, which is called tilt. Okay? And then you have a rapidly varying exponential here, which gives you most of the behavior that one would be interested in. The way you can see what this behavior is you take a stationary phase of this exponential here, and you have to do a few more tricks. You have to expand this exponent and resolve the delta H into a spectrum. When you do all that, you find what you get is Bragg scattering from a tilted plane. To lowest order, say if you take the projection of the wave vector that characterizes the surface, that'll be the same as Q here is the difference between the incoming and the outgoing wave. Okay, so that projection onto that same tangent plane. Okay, so yeah, I mean, everybody's seen that in one form or another. It may not have looked exactly like this, but it's just tilted plane scattering. Now, usually, or very typically, the reference surface, of course, is very close to the z-axis. And so we get the magnitude of the surface wave vector is very close to this value Q here. And that's why we call Bragg waves, of course, when this kind of thing is true. And the cutoff is still a free parameter, and typically in experiments, we find that this cutoff values between a half and a third works reasonably well. Okay, so that was the state of the theory as of a couple of years ago. And what are the problems? Well, actually, not a bad theory. Couple of things that were still outstanding problems. One is that the small slope theory is okay as long as the grazing angle is not too shallow, but at very shallow grazing angles, there basically breaks down. And the reason you do that is you can't really neglect the higher orders of the slope. Okay, the composite model had quite a few problems with it, although in general it's somewhat better than the small slope result. The composite model is not really the result of a self-consistent formalism. I mean, like I say, you say, well, okay, sort of you replace the z-axis with the normal. And you really want to do a little better than that. You want to say exactly what it's an expansion and which parameters have to be small for it to be good. And you also want to systematically improve it. Say it's a first order approximation, well, what's the second one? That kind of thing. Another problem is it's not always easy to choose a cutoff. And particularly, as I'll describe later, at shallow grazing angle, it turns out that the cutoff is angle dependent, and just effectively, then it's just no longer a useful theory either. I should also say that there was some controversy back when we first got on this problem as to how big these cross sections really are. So there's a great deal of motivation to go back and look at scattering theory carefully. Okay, so now I'm going to try to describe the new formalism here, and I'm going to stick to this same problem I've been discussing up to now for the time being, the Stairs-Chalet problem. Okay, and the first step of the new theory really is to develop a formalism for perturbations around a smooth surface. In other words, I'm trying to give people, or trying to derive here a formal statement of the composite model. Okay? Well, the idea of the composite model, formally, is that, okay, you have the solution, which you know well, for some reference surface S, 0. And you want to find the scattering amplitude for some surface which is in some sense close to S. And the sense that we mean really is that if you take the normal from one of the surfaces and find the distance to the other surface, that quantity is going to be small in some sense. Okay? So formally we can write that this way. I'm going to claim that this quantity can be expressed in terms of a formula that looks like this. Okay? And I'm not going to give you the gory details of the proof, but I do want to give you an idea of what the basic ideas are. And there's really, remarkably general things that just go into it. You start off with these very general forms, really, for the asymptotic solution. And all you say is that these asymptotic solutions have to obey the Helmholtz equation in the asymptotic limit. Okay? And these two solutions will satisfy boundary conditions on S1 and S2. Okay, for right now, I'm going to assume again the Dirichlet boundary conditions. We'll relax that later. And that they both correspond, again for right now, I'm going to assume they correspond to the same wavelength. Okay. Now just consider this quantity here. That's a little bit like a generalization of a current. It's phi1 grad phi2 minus phi2 grad phi1. And we find that the divergence of this thing is 0 because these quantities both satisfy the Helmholtz equation at the same wavelength. Okay? And whenever you see a quantity with a divergence of 0, of course you can always use Gauss's divergence theorem. Let us integrate over a whole volume, and then that's just going to be equal to the surface integral of the vector on the boundary of the volume. And in this case, we're going to choose the boundary of the volume such that it's going to be S2, this thing up here, and the sphere at infinity. Or, of course, if you're doing scattering for an infinite surface, it'll be a hemisphere at infinity. Okay. And what you find is, okay, this is the contribution of the surface integral from the sphere, and this is just what you have at S2. Now remember, we chose phi2 at x2 to be 0, so this thing here we can forget about. And this quantity here, we can use stationary phase, which becomes exact as you go out to infinity, to evaluate this, and this will just be the difference between these two scattering amplitudes. Okay? Now, the next thing you want to do is you want to express this. Right now we have phi1 at x2, and you want to take advantage of what we know about the boundary condition on phi1. So you want to express phi1 somewhere on S1. And the way you do that, as I said before, is you start out at S2, you draw normal to S2, and you start at point x2. You just follow that normal up until it intersects S1. This will be a new point x1, and we'll define that to be x1. Again, when we say the two surfaces are close, we're assuming this quantity c here is small compared to other linear parameters in theory.
Compared to the wavelength of the wave.
Wavelength of the wave. So then phi1 of x, just 0 by the boundary condition, and we just expand the first order, and this will be quantity will be c squared. And yeah, I mean, you can get an idea of where the wavelength of the wave comes from. I mean, just it's 0th order. This is just a plane wave, so you just get a k that comes down. So it's c times k.
So you really think of your S2 as an analogy with a composite model. You think of your S2 as the long waves, and S1 is going to be the short Bragg waves. Or
yeah, that's going to be
just the sum of the Bragg waves plus the long waves.
That's right. S1 will be maybe the rough surface, and S2 will be the smooth surface. Yes, and in fact, we're going to eventually be letting this c become infinitesimally small. Okay, so when we make this substitution here, what we find is that P1 minus P2 is just this thing here. Now one thing is, of course, if you choose the two surfaces to be the same, then you just get the reciprocity theorem right out of it. And when we use the reciprocity theorem,
Put that back up again. That final
Okay, the final equation there, that looked like the one you had in the previous sheet, your hypothesis. Right?
Yeah.
But that is an approximation based upon a perturbation expansion.
That's right.
Okay.
That's right. And that formula I put up there is first order in delta H.
Okay.
But it's good to all orders in S0. It's only first order in a perturbation, but the formula is good to any order for the solution.
Yes.
So when you use the reciprocity theorem and you make this substitution here.
When S2 was rough enough to have multiple scatters?
Pardon?
Would it handle an S2 that was rough enough to have multiple scatters?
I think that's when you start to run shadow.
Overshadowing.
Yeah, you don't want shadow multiple scattering, at least not yet. Now, what we'll do is, in a little while, what I'll do is I'll take this thing to be infinitesimally small, and use that to generate a formula for the scattering amplitude, which should, in some sense, naturally handle shadowing more easily. I'll explain why that happens.
Do you need shadowing for your multiple scattering, or do you get multiple scattering even when you don't have shadowing?
Well, they're both similar effects. They're both basically non-local effects.
S2 is a known solution.
Pardon?
Is S2 a known solution for a known surface in any sense?
Are you assuming here, again, just a known solution for an
Absolutely. Yeah, and I mean, if you know a solution that includes multiple scattering, there's nothing in here that says that the solution on S2 can't include multiple scattering or shadowing. Really, formally, we're just saying, okay, this is an exact solution on S2. Let's see what happens when we perturb S2 by a little bit.
Okay.
So that's really all that's going on. These are given, and there's really been no assumption of how good those results are. We assume they're absolutely.
So I do some sort of geometrical optics or acoustics calculation to get the field on S2.
Exactly. Yeah, I'll give some of the details on that. Yeah, and then of course, for those specific cases, once you start doing the geometrical optics calculations, and then you have to be careful. Then, implicit in geometrical optics is that you're neglecting things like the curvature, and implicit in that is that no, you don't have multiple scattering. But so far we haven't done that. So far these guys here. Okay, so yeah, now we're just a step away from the hypothesis. Once again, we had this thing was a solution on S1 and S2. We can replace it with a solution on S2 again to this order here. And we now, since it doesn't matter, we can drop the subscripts S1 and S2 because everything will be the same to this order. Also, if you stare at the geometry long enough, you'll find that C and a vertical displacement delta H are related by this formula here. NZ is just a Z component to the normal. And that the surface area elements are related is given by this formula here. When you substitute that back into the formula here, you get my hypothesis. And this is a formal expression of a composite model, as I've said. These guys are exact solutions. They should be good. And you just assume that they're good for all orders for S0, which now we know S2 for S0. And what we call the traditional composite model, we then get out of this by neglecting the curvature of S0. And it turns out that this is really a very powerful theorem. For one thing, we really only assumed that B is a constant in the asymptotic limit. And we used the Helmholtz equation, but we didn't assume that it wasn't spatially dependent. Wave number 10. Well, the first consequence of this formula for the perturbation is we can derive a new expression for the scattering amplitude. And what motivates this is we look at this formula for the change in the scattering amplitude and say, this manifestly exhibits reciprocity. It's a really nice formula. On the other hand, our old formula for the scattering amplitude doesn't. And so we suggest, well, can we use what we've learned about delta t to generate a representation for the scattering amplitude that in fact behaves correctly? And it turns out, yes, you can. And the idea is you move your surface S, or equivalent to the origin, by distance negative d, and this d here is infinitesimally small now. Okay, well, that's the same as a coordinate transformation, r to r plus d, and of course the distance then is given by this relation here, and the same functions you make any time during the asymptotic limit. Basically what you do is you find that your wave function changes by, well, there's an overall phase that it changes by, and then your scattering amplitude changes by first order in d and negative I q dot d. Okay. Well, then what you do is you say, okay, but this is exactly the same as moving the surface S a distance negative d. So we just let this c in our formula before equal negative n hat dot d. And you get this expression right here, just combining these two different ways for seeing what an infinitesimal translation will do. In other words, though, this d here now is an infinitesimal translation in an arbitrary direction. So you get this kind of a vector equation here. Okay? Now, for this talk, I'm going to just assume that the z component, we're just going to take the z component of this. And I really haven't had a chance to look at the full vector equation, which is some interesting issues that's not showing up there when you have flat plates like that. But, yes, for now, you get this kind of an equation for t, and once again, it manifestly shows the reciprocity. Okay? This is really going to be the first ingredient of our new theory here that we're going to establish. And as I say, manifestly exhibits reciprocity at each order. And the second thing is, no real assumptions went into deriving this thing as far as shadowing or multiple scattering. So that, in a sense, shadowing shows up naturally if we want to develop a very simple model where we say that we just blot out the areas that are shadowed according to geometrical optics. You can do that in the sense that it's symmetric between an incoming and an outgoing wave. So, you can use the full geometrical optics description to put that in.
When you say you're looking at the z component, the outgoing wave is probably perpendicular to the surface or something?
Oh, no, I just took this vector equation right here and multiplied by c. Q could be anything. Could be anywhere.
It's coming down from the right direction.
Yeah. Now, of course, if you have a half, a half plane kind of a surface, then the outgoing and the incoming have to be in the half plane too. And have it. That's all. Oh, got my slides. They're order mixed up. Okay, now, there's a second ingredient here, this new formalism, and that's a new iterative formula. Now, what we do is we use the fact that if p is a constant on the surface S, then the gradient is going to be proportional to the normal. Okay? So that means then that for an arbitrary vector m, as long as, of course, they're not at right angles to the normal, this kind of equation here will hold. Okay? And you can derive a new iterative formula for the normal derivative of the solution evaluated at the surface. The same way you derived the original one, you take m hat dot grad of the formula for this guy. So there's an integral formula, and you take limits and so on, and this is the iterative formula you get here. Now, what I do in this formula is I let m hat first equal z hat. Well, then it turns out that the kernel here is going to be anti-symmetric with respect to an exchange of x and x hat. And it's going to again be proportional to this difference between these two values, evaluated at different points. Which means that it's going to be order of, again, of the derivatives in higher order. Okay, now the first order in H cancels when we compute the scattering amplitude. So we get the small slope result. We haven't done anything. We just substituted straight into the symmetric formula for t. None of the business of taking iterations, expanding, and so on. Now, if we let m hat equal n, the normal for a reference surface, well, we get the composite model result that comes right out of it without any iterations either. And the way we can see that is that we see that the kernel turns out to be anti-symmetric up to first order in the curvature. And now what we've done is we've also found basically that this is the expansion parameter in the composite model. In other words, that the error will be first order in the curvature too. Okay. And I should. So we say note the trade-off you get between the composite model and the small slope. What you really gained is you've taken the slope of the reference surface out of the expansion, but you paid for it by going down in order in the curvature. Okay. And that's maybe one nice thing about this formalism now is we have a nice way to compare these different expansions, see what the trade-offs are. And the advantage of different kinds of expansions, when we expand the derivatives, this is better than the Born series already. When basically that exponential we had before was in there, we improved it, got the small slope by taking QZH out of the expansion. Okay? Well, similarly, supposing we could take grad H, a little bit like here, out of the expansion, and just have an expansion of curvature, then we would expect to have an even better approximation. And basically the idea is that you have less and less information in the higher derivatives. So you can get sort of a hierarchy of better expansions just by taking out smaller derivatives of the surface. Okay, well, how do you do that? Well, you let m hat equal to normal. Okay. Now, the kernel is anti-symmetric up to first order of curvature. So, without any iterations, we expect this thing to be bad because, especially for small waves, when r is small, we're better off going to second order in the slope and in this lambda over r, rather than hanging around first order with these derivatives. I mean, maybe the idea is that the curvature term is not going to be a lot less than the slope. But on the other hand, if you go through one iteration of this, you're going to find an error is square in the curvature. In other words, it's really better than the small slope because you've taken the slope out of your expansion. Okay? And also, it turns out if you stare at the formulas long enough, it really should be able to recover the composite model without the use of a cutoff. In other words, you go into this answer right here, you let h equal h0 plus some perturbation, you drop the curvature terms for the big waves, and you wind up with a composite model, but you never really had to assume when you first wrote this answer here that you had a cutoff for anything. Okay? So the next step is to find an expression for this scattering amplitude here that'll give us this kind of an error. And of course you could go in and you could take this kernel and do one iteration and so on, and that really, really turns out to be a big mess. But there's a shortcut. And the shortcut, the way you do this is, again, you go back to this formula for the perturbation. And you can use that to generate this answer. And effectively what you do is you use the fact that it has to reduce to the composite model in order to get it. The first step is you have to prove that the result you want is of this form, just a function of the gradient times the exponential we had in the small slope model. And I'm not going to go into the details of that. It can't be done. It's just a question of sitting down and carefully looking at what the general expansion is and how you integrate by parts to get out the terms that are second, they're basically second order in H. I mean, second derivatives in H, basically curvature terms and so on. Okay, now, if we do the composite model hypothesis, replace H with H0 plus delta H, and expand this to first order in delta H, we get this kind of an expression for the change in the scattering amplitude. Okay? Well, and then the idea is you want to get rid of this here, so you integrate by parts, and once again, you drop the terms that are proportional to grad of H0. In other words, what we're doing is we're really reproducing the traditional composite model. Okay, so we have one expression for delta t here. Okay? Now, we can also get the traditional composite model by doing what we were discussing before. Go back to our symmetric formula for t. Put in these values for n dot grad p that are good to first order in the curvature. Okay? And you can either do that by going back to the iterative formula or use general arguments. As to that, if the curvature disappears, geometrical optics has to be exactly the correct answer. At any rate, you get this second expression for delta t. So once again, as we got the symmetric thing by considering both the new expression for the change in the scattering amplitude and calculating it a different way, we do the same thing for here. We equate these two equations, and we get this kind of a differential equation for this g here. Okay? And I've dropped the subscript 0 because it's not doing anything to the subscript. Okay, C is just a gradient of f. F was just the thing that was up with the exponential. Q dot x. Well, I'm not to repeat that anyway, so that's it. And this is just an ordinary differential equation. So that it really only depends on the magnitude of C. The direction of C doesn't even show up in the equation. So what we do is we express the normal as a function of this vector C, and we can just integrate this ordinary differential equation. And we set the constant integration by requiring smoothness at the geometrical optics limit. And the reason for that is that kinks in G would contribute, it would give us high frequency contributions, but just no reason to include them at this point. So we don't. That sets the constant integration. Okay, and just so you see one of these solutions, what it does is it gives us a formula here for scattering amplitude. It's in closed form, and involves an arc. And again, just the same thing that you had for the small slope result. And it's expressed in terms of these two new vectors. We have the capital Q we had before, and also a W, just in the normal components of those. And you can verify by comparing this guy to exact solution, for instance, the sphere. And I think one of Professor Dashen's graduate students has actually sat down and calculated this and found really very good agreement. Another thing you can do is just go back and make sure you solve the integral right by making sure that it in fact does reproduce the composite model without any cutoff. Now, we see that this result I just wrote there and the composite model are in a sense related in a very profound way. But they both share a certain problem, and it's kind of interesting to see where that comes from and how you get around that. And that's basically if you have a fractal surface, and the problem we were interested in, the ocean surface is such a surface, then you've got special problems. And the problems really come from the fact that grad H is not defined. In other words, you can't write the normal anywhere on the surface. Now, it's a little bit easier to get around this and see what's going on if you assume that if you ensemble average the surface. And just briefly then digress for just a minute here and just roughly say when we ensemble average, we do what's called a Gaussian assumption, which basically means that we assume a random phase between spectral components of the surface. And that means basically that this quantity here, the autocorrelation function, gives us all of the statistical information. And very often we're interested in the spectrum, which is simply the Fourier transform of the autocorrelation function.
Can I ask a question about that? When you take a surface of the ocean, you take a Fourier spectrum of the pond, you find it's highly correlated. I mean, it has some kind of autocorrelation. What are your random... I'm not familiar with these procedures, so I don't know what the random phases are between. For example, if the spectral components are very close to each other, then they're all Aren't they phased very close?
Well, what you assume is that the source of the wave is very far away. They've all been propagating dispersion along this. I mean, I don't know. This comes out of Owen Phillips' book. It's apparently experimental on Gaussian assumption. It's legitimate. It's legitimate for that reason. Because the waves have prolonged this. I mean, it's not an aspect of the problem I'm terribly familiar with. It's strictly something that in the literature seems to be consensus that this is a reasonable approximation.
No, but the spectral components of the surface are continuous Fourier K. Which one of those are random to the other? Is it f of k is random as you change k by delta k? I don't understand.
I think the models that I've seen is you say, well, okay, you use box normalization or something like that, and you have then a discrete spectrum, and then each of the phases separately are assumed. Yeah, I can't vouch for this. I mean, this is in the literature. I could give you a reference for it. It doesn't seem to be an object of much controversy.
Okay.
Okay, so with this two-scalar arctangent formula that I described, what you get is you get this kind of expression here, k over, well, these kind of things here. And of course, the big problem we see right away is if the surface is a fractal, these surfaces are not going to be defined. And one way which it shows up is when we do this ensemble averaging and we work in transform space, we get wave numbers here that cause our expectation value here to blow up. Okay? So effectively what happens is you've got basically all kinds of wave numbers. You've got wavelengths of, when you make up the surface, you've got arbitrarily short wavelengths that make up the surface.
Your S of k isn't decaying fast enough.
It's not decaying fast enough. Which is, yeah. And you can patch that up by saying, okay, well, you have an upper cutoff. I mean, at some point, these very, very short wavelengths really can't contribute. But as I said before, the problem is when your grazing angle becomes very shallow, these things here become infinite, and even a cutoff isn't going to help. You have to do that cutoff depending on the angle, and that's not easy. I mean, well, it's not easy. It's not practical to do that. And so, you want to find a better way to do that. We have to ask ourselves, why are we running into trouble? Because the small slope was fine. But the small slope basically depended on h of x minus h of x prime here. And when we do the iteration, the small slope is really an expansion of this. And what we went then and did is we took this h of x minus h of x prime and we peeled off grad h of x. Okay? And the bad terms, the ones that are giving us the problems, are second order in grad h. But we're not considering second order in the second derivative of h. So that basically these infinities that we're leaving out here have to cancel what we left out here. So you really have to go back now and you say, okay, you have to go back and do a full second order expansion of difference of this. Just take 2 full iterations and get an answer. And sure enough, that works. And to very briefly run through it, you can generate an improved composite model by finding a value n dot grad pk. This is the integral equation. You do 2 iterations. You make a few common assumptions in these 2-scale models, and you get something that sure enough has a finite value without any divergences. But then you have to go back and make a few more approximations, which put your divergences back in, but they're not as bad as they were before. And final answer looks like this. And really what you can see when you go through the details of this is, see, this thing here looks like it diverges, but it doesn't really, because you have as these L's become arbitrarily large, you have an I times L and I times L in my signs. Since cancel. So you have minus L squared plus L squared. This is well behaved. And what's more, it's well behaved in the sense that if you left out the L squares here, you get the same value for the integral. And it turned out when we were doing the approximations, there's a similar kind of a cancellation we left out this term down here. Okay? So this divergence is nicer. You don't have this k over kz dependence that blows up, so it's not angle dependent. And also it turns out, as we got a hint of up here, this guy down here, you look at the cross-section and evaluate it, all the physically relevant things is this long flat area before the L squared kicks in. So that effectively you just take all of the L squareds out of it, that you'll get the answer that's should be correct. And that's really not very sensitive at all anymore then to the use of a cutoff. And it turns out that this result is in fact good at shallow grazing angles, and we've had a chance to check it. There's some very nice work that Eric Dorsos has done up in Washington, where he just really studies these one-dimensional problems very closely. And he goes up to fourth order perturbation theory and studies lots of realizations and triple checks everything and finds he gets the same curves. And his predictions for the correction for small slope really are very close to ours. And remember, all this comes on top of an effect that's already, fairly significant. So that we're talking about around 1% of a 1% correction. So 2% correction, 3% correction. Ours, we do somewhere hidden in our thing, we do assume a small grazing angle. So our result is somewhat closer at 10 to 20 degrees incident angle, and there's no real shock. But it's even there, it's not sure. Implicit in our assumption is that we do include some higher order terms than fourth order, so it's not really all that clear. It's really better. Okay, I'm just about out of time here. So I'll just very quickly run through and sketch how you can generalize this whole thing to, say, a scalar field with arbitrary boundary conditions. Now, as I said before, you can assume that V is constant in the asymptotic region only. And when you do, then all of these wave vectors here, you just evaluate in the asymptotic region. Once again, you assume the general asymptotic form and arbitrary boundary conditions. And comparable to what I had before, you get this kind of a master formula. Okay? Where before we had just this and this down here. And now you get all these other terms. Effectively, a good way to look at it is this term down here corresponds to the Neumann boundary condition problem, where you assume that the normal derivative of the field is 0 on the boundary. These terms here reflect changes in the boundary condition between S1 and S2, or change the boundary condition for the solutions phi 1 and phi 2. This curvature term here, well, it's related to the fact that we used one surface to define the surface area of the other surface, so that I had to define this average area here to the average of these two surface areas, and that way I get an answer here that's actually manifestly anti-symmetric in these change of 1 and 2, as the left-hand side here is. And once again, you just make all of the substitutions you can get for any of these boundary conditions here, including just the general impedance boundary, you get the reciprocity theorem. And so, yes, this lets you do a particularly interesting or particularly useful exercise, something with the Neumann boundary condition. Okay, and you can also do, just very briefly, a two-fluid interface. All that's involved there is you use the continuity of the field and the normal derivative of the field, patch together the two solutions on the two sides, take the difference, and you get formulas for the change in the scattering amplitude, both reflected and transmitted. You do it right. To get transmitted, one has to have one of the incoming waves coming from the bottom, effectively. And also, just so you know we did it, the electromagnetic field, you can do the same kind of thing. Here you assume an isotropic medium, no free charges, but you don't assume necessarily it's homogeneous. I mean, these things can, again, outside of the asymptotic region, they can depend on the location. And once again, you get a very similar formula for the change that we got. We had that. Turns out you get terms in addition to the curvature terms I said before and so on. You get terms that involve products of the normal components of E and H, or the tangential component of E and H. This will correspond to a perfect conductor boundary condition, in a sense, be its conjugate kind of thing. And just a very similar analysis you can go through, and you can find small slope composite model. And in fact, also the expansion and curvature, the same kind of thing. I mean, you can do that. We have done that. We've gotten back to these boundary conditions. We've gotten sort of corresponding arctangent formula, the one you saw before. Okay, so finish up here. I think just to review once more what we did. The engine that drives the whole theory is this formal description of the composite. Everything really flows from this. We used that to get a new expression for the scattering amplitude that manifestly exhibits reciprocity. And then that allowed us to recover the small slope composite model results for what I know of existed for the Dirichlet condition. We've been able to go on and do the Neumann, the perfect conductor conditions, as well as the interface using the continuity requirements. And as I just mentioned, you got new expansion and curvature. And finally, the future, some things we've already done, but I can't really discuss at this talk, is you can use this kind of thing for the change in the scattering amplitude to see what happens if, say, whether the results are of a change in these kind of constants. Here, say, a change in the index of refraction between two fluids. How will the scattering change? You can also do that for, say, a cloud of point scatterers underneath the surface. The first order, again, there you have to expand in the wavelength times the depth. And you can reproduce the optical theory if you like by going through the same analysis except with the complex conjugates.
Questions? How far along are you on the electromagnetic problem?
Well, we have these expressions, the small slope, the composite model, and the arctangent formula, and we have the master, the equivalent of the master formula. I don't know if you're interested. I can flash up the picture of the.
I don't think that's not for this question. And then for the electromagnetic problem in terms of validating it, are you present?
We haven't done any of that.
The validation that you described was with the acoustic problem. Yeah. Are you planning to do that for the electromagnetic problem?
Time to time. Very nice.
Any questions? Thank you.
Nervous moment there.
I was trying to think back to something that you said about halfway through.